So hello everyone, today we are going to start with chapter 2. Before that we will complete the final and the last theorem in chapter 1 that says that if f, capital F, is a primitive of f, small f function in omega, and gamma be a smooth curve with ends w1 and w2, suppose that w1 is the starting or the initial point of gamma and w2 is the ending point of gamma. Then the integral along gamma of f of z is equal to capital F at w1 minus capital F at w2. Moreover, if gamma is closed, then the integral over gamma of f of z dz is equal to 0. This is clear why, since if gamma is closed, then w1 is equal to w2, and so f of w1 minus f of w2 is equal to f of w1 minus f of w1 equal to 0. The proof is very simple, as you see here. Integral over gamma of f of z dz, following the definition, is equal to the integral from a to b of f of zt z prime t dt. Now we can replace f by capital F prime, since f is capital F is a primitive of f, and we write the integral as follows: integral from a to b of capital F prime zt z prime t dt. Now this term here, replace it by following chain rule: d over dt of capital F at zt, and following the if you invoke the the fundamental theorem of calculus, you find that this integral here is equal to f at za minus f at zb. Za is equal to w1, zb is equal to w2, the final point of curve gamma, and you get the desired formula. Corollary: if f is holomorphic in a region omega and f prime equal to 0 over omega, then f is equal to constant. The proof is very simple also. Take the w0 in omega and let w be an arbitrary one. So fix w0, and for any arbitrary w, choose gamma. Of course, gamma depending on w, so that we can assume that, without loss of generality, that the segment joining these 2 points is also in omega, since omega is connected by assumption. And so integrate then over omega over gamma of f prime. F prime is equal to 0, so the integral is equal to 0. And using the previous theorem is on other hand equal to the primitive of f prime, which is f at w, the final point, minus f at w0, the initial point of gamma, which implies that f of w is equal to f of w0 for any w, and so and consequently f is constant in the region omega. Now we will start with chapter 2, Cauchy's theorem and its applications. First, very important theorem, Gorset's theorem. It says that if omega is an open set and T is a triangle with boundary contained in omega, then integral over T of f is equal to 0 for any holomorphic in function f in omega. So the proof, we will call the initial or our initial triangle T0, and we will bisect it to, as you see here in the figure, in figure 1, to get 4 triangles T11, T12, T13, and T14. The bisection is as follows: take the midpoint of each segment in the first triangle and join them, and you obtain the desired triangles. Let D0 denote the diameter of the initial triangle T0. P0 denote the perimeter of the initial triangle T0. We have star, the integral over T0 of f is equal to the integral of f over T1 plus T11 plus over T12 plus the integral over of f over T13 plus integral over f over T14. Why? Because, for example, if you take here this segment and you need to integrate in this sense and in the reverse sense. So, and these two integrals will cancels out, so you will finally obtain that the integral over the initial triangle is equal to the integral over these four triangles here. And star implies that the modulus of f at t0 of the integral of f at t0 over t0 is less than or equal to 1 over 4. Here we have four terms, so integral of not 1 over 4 to equal to 4 modulus integral over t1j for some j, one of them. J, t1j is one, of course, one of them of these four triangles. So j belongs to 1, 2, 3, 4. We will call t1j t1, and we will denote by and let d1 denotes the diameter of t1, p1 denotes that perimeter of t1. Here we have d1 is equal to 1 over 2 d0, p1 is equal to 1 over 2 p0. So continuing in this manner, so bisect t1, you will find that finally continue bisecting. So at the nth bisection, you find that the modulus of the integral of f over t0 is equal to 4 power n modulus integral over tn of f d0. And if pn denotes the parameter of tn and dn denotes the diameter of tn, then pn satisfies the following pn and dn satisfy the following two relations here, or two equations here. Now let τ1 be the closed solid triangle with the boundary tn. With boundary triangle tn. It's clear enough that τ0 contains τ1, contains τ2, and so on. And the diameter dn approaches 0 as n goes to infinity. Then by a proposition in the previous chapter, we find that there exists a unique z0 belong to these tau n solid triangles for all n. And since f by assumption is holomorphic, at z0 we can write f of z equal f of z0 plus f prime z0 plus psi z minus z0 of course. Here psi z tends to 0 as z tends to z0. Now the integral integrate both sides over tn. Since f of z0 is constant, f prime z0 at times z minus z0 here, the first two terms are holomorphic functions. Their integral will be 0 over the closed triangle tn. And finally, we obtain that the integral over tn of f is equal to the integral of psi z over tn of psi z times z minus z0. Now we have modulus of z minus z0, of course, less than or equal to d and the diameter of the triangle tn. Then modulus of the integral over tn of f is less than or equal to epsilon n d power n, or sorry, dn pn, where epsilon n is equal to what? Equal to the sup of psi z. Z belongs to tn. So epsilon is a constant depending on psi and n, of course. And tends to 0, of course, as n approaches infinity. This implies that for n, so modulus of the integral over t0 of f less than or equal 4 power n modulus of the integral over tn of f less than or equal 4 power n epsilon n dn pn less than or equal 4 power n epsilon n dn is equal to what? 2 power minus n d0, and pn is equal to 2 power minus n times p0. So here we will write 2 power minus n d0, 2 power minus n p0 less than or equal to 4 power n minus or times 4 power minus n epsilon n d0 p0. This term here is equal to 1. This term is a positive constant, and this term tends to 0 as n tends to infinity. So finally we obtain that the integral, the modulus of the integral over t0 of f equal to 0, and the integral finally over t0, the initial triangle of fz dz is equal to 0 as xi. This is Gorstat's theorem. Very important theorem. We'll see many applications later on. Two, Cauchy's theorem in a disk. A holomorphic function in an open disk D has a primitive in that disk. So proof, without loss of generality or translating if necessary, you will assume that that disk D is centered at 0, and let Z belongs to D. Okay. Suppose that Z is here. And take this path from 0 to Z. Look. Go to re Z and then to Z parallel to the y-axis in this way, and call this path omega Z, gamma Z. So here re Z, here is Z. Go from 0 to re Z, and then from re Z parallel to the y-axis. And call this curve omega Z. Now, gamma Z. Now, let f of Z, capital F Z is be equal by definition to the integral over gamma z f of w dw. Our definition of omega z makes this integral unambiguous, and well defined. Now let h be small enough so that z plus h belongs to d. H small or sufficiently small. Compute f of z plus h minus f of z. Of course, this is equal to, by definition, integral over gamma z plus h of f of w dw minus integral over gamma z of f of z, f of w dw. Now let's see the final integral over which path. This integral here over omega z plus h over gamma z plus h. This integral here over omega z. Let's write this difference here as an integral over some curve. Okay, so we'll start with the first case, or the first graph. We have in figure A the integral first over z plus h. Suppose that this z plus h this is 0, this is z plus h, and this is the integral, the curve omega z plus h, and this is the integral over, and this is omega z, this is z, and this is gamma z, sorry. Now we are integrating about over omega z plus h and over the reverse direction of omega z. So since we have a minus sign here, so the integral, we are integrating over these two curves here. So this part, we will get rid out of this part, and we find that we just need to integrate over this part here, the left part. Now you can complete this figure. You can complete this figure and add the following segments. I will add them in red. I will add them in red. Add this direction, left, right, and this direction in opposite senses. You're still integrating over B. You're still integrating over B. If you add these two segments with in opposite directions, you are still integrating over the curve in the second case B. But integrating over the curve in C is equivalent to integrating over the part here. Since the integral over the triangle above is equal to 0, here over this triangle is equal to 0, And over the rectangle also by Gauss's theorem, you can bisect you can write a rectangle as a union of two triangles, and so also by Gauss's theorem the integral over the rectangle below is equal to 0. So this keeps only one direction, or the one segment, or the segment here. Finally, we are looking, or we are integrating over this segment from z to z plus h. Call it eta. Call it eta. Now we can write the sum, or the difference, f of z plus h minus f of z equals to the integral over eta of f of w dw. And f of w can be written as, since f is continuous, as f of z plus h psi z, where psi z tends to 0 as h, sorry, psi w, where psi w tends to 0 as h tends to 0. This implies that of course the integral over eta of f of w dw is equal to integral of f of z over eta dw. This is constant. You can pull it out of the integral, and we obtain f of z times modulo times h, and this term cancels out when h tends to 0, plus h integral over eta of omega w of sorry psi w dw. Now we obtain that 1 over h f z plus h minus f of z is equal to what? This term here, if we divide it by h, we obtain only f of z plus integral over h over h at eta of psi w dw. Taking h to 0, this integral tends to 0, since psi w tends to 0 as h tends to 0, and you find that limit as h approaches 0 of 1 over h f of z plus h minus f of z is equal to what? Equals small f z, small f at z. And we conclude that capital F is differentiable with f prime z equal to f is holomorphic, is differentiable in the complex sense, and f prime z is equal to f of z, and the function, the capital F function defined previously, is the primitive of the holomorphic function f we have in the theorem, and we are done. Now we conclude that if f is holomorphic in a disk, then for every gamma, a closed curve in that disk, that integral over gamma of f is equal to 0. Why? In fact, we are joining all the previous results in this statement. So if f is holomorphic in a disk, then has a primitive, and if f has a primitive, then its integral is equal to 0 over any closed curve, as we saw before. Now 3, Cauchy's integral formula. Suppose f is holomorphic in omega that contains a disk D with its closure, with its interior. And let's see, denote the boundary of D with positive orientation. So C is the boundary of D with positive orientation. Then f of z is equal to 1 over 2 pi I integral over c of f of psi over psi minus z dz for all z belongs to D. So this result is very powerful and relates the values of f in a disk with the integral along integral of f along the boundary of the disk. Proof. Let z belongs to D and consider the keyhole so this is the disk, this is Z and the disk D, and the keyhole is as follows, can be drawn as follows. Let the Z so this is the keyhole obtained from from the disk D, where delta here is the width of the corridor and epsilon is the radius of the circle around, call it C epsilon, around Z in negative direction. Let f, capital F, psi is equal to f psi at psi minus z, psi minus z. This function is of course holomorphic away from the point psi equal to z. So this is holomorphic away from the point psi equal to z.